Okay, so now we continue to chapter 2. We're going to talk about uh, minimal variance unbiased estimation. As we said before, we the design of estimator is actually a design issue. For a design issue, then you could have a lot of different choices for designing an estimator. And in this section, we're talking about minimum variance. So imagine this, you have a whole possibility of doing estimation, right? In terms of the functional forms, you have a lot of possibilities. And this is a set of estimators. We're talking about minimum variance unbiased, which could be a small subset of the estimator. It's just a small subset, and you could have other choices. Okay, so we will begin our search for good estimators of unknown deterministic parameters. So notice that it's unknown and deterministic. We'll restrict our attention to estimators which on average yield the true parameter value. So on average, we're talking about on average, yield the true parameter. Then within this class of estimators, the goal will be to find the one that exhibits the least variability. To find the one that least variability, meaning that what we want, uh, we like it to be more concentrated on the true value. As we did before, we like it to be more concentrated, the variability to be smaller. And hopefully the estimator that's obtained will produce values close to the true value most of the time. Okay. So we'll talk about unbiased estimator, and also Kramer-Rao bound, and then uh, minimum variance is solved. So within this class of estimators, the one with the minimum variance is solved. A further constraint on the estimator is the linear of the data. Okay. If we constrain our category to be linear in the data, then it will lead to an easy implementation but suboptimal because you have more constraints. Okay, so let's start unbiased estimator. For an estimator to be unbiased, we mean that on average, the estimator will yield the true value of the unknown parameter. When we say on average, we are actually talking about expectation of something. Okay, so since the parameter value may be in general be anywhere in the interval, unbiasedness asserts that no matter what the true value of theta, our estimator will yield it on average. Mathematically, an estimator is unbiased if expect of that theta hat is equal to theta for every value, for all possible value of theta. And AB often denotes the range of possible values of theta. Okay, so unbiased estimator for DC level in wide Gaussian noise. Example. Okay, so we consider the observation, the DC level problem in wide Gaussian noise. Consider the observations xn equal to A plus Wn, and for n is 0, 1, all the way to a minus 1. This is the time index, time index, where A is the parameter to be estimated, and Wn is Wgn. The parameter A can take on any value in the interval. Then a reasonable estimator for the average value of xn is, as we did before, we come up with the estimator A hat equal to n divided by 1 divided by n summation xn, or the sample mean. We call it sample mean. Due to the linearity properties of the expectation operator, you take the expectation, you get E of this 1 over n summation x, and then equal to 1 over n, because the linearity, meaning that you can take it out. And then summation, you can pull the expectation inside. So you get expectation of this, and then summation and n are all outside. And then it will be 1 divided by n summation a, right? Because this expect of xn, let's see again. If you take the expect of xn, this has 0 means. As a result, it will produce a. So that produce a. And then summation of a, again, is NA, divided by n, which then it becomes a. The sample mean estimator is therefore unbiased. In this example, A can take on any value. Although in general, values of unknown parameter may be restricted by physical considerations. Then estimating the resistance, for example, would necessitate an interval of 0, large smaller than r, right? The resistance is always larger than r, larger than 0. And then unbiased estimators tend to have symmetric PDF centered around the true value of theta, although this is not necessary. Okay. For example, if we want to take on this example, the PDF will be NA sigma square divided by n. The restriction that expect of theta hat equal to theta for all theta is an important restriction. Letting theta hat equal to g of x, where x is equal to that. It asserts that expect of theta hat equal to integration g of x p of x theta, a condition on theta dx equal to theta for all theta. So I think this is a critical formula. If you take the expectation, then g of x multiplied by that has to be equal to theta, the expectation. That's the unbiased estimator. Okay, so probability density function for the sample mean estimator. So this is what we say here. It's a concentrated around A with sigma squared divided by n. So it's sigma squared divided by n. It is possible that may hold for some values theta, but may not for others. So here, let's talk about another estimator. So, bias estimator for DC label. We consider again, recall, we consider again that signal model. And then our intention is to design another estimator. And it could has different property. So modify sample mean estimator. A delta equal to 1 divided by 2n, and then again do the summation. Then what happens is A delta is equal to, again we do the expectation process as we did, then it will be A, the whole thing is still NA, right? Still NA. And for NA divided by 2n, it becomes A divided by 2. 1/2 multiplied by A. It will be equal to A if A is 0, and it will be not equal to A if A is not 0. So it will be seen that this holds for modified estimator only for A is equal to 0. Then clearly A is a biased estimator. Okay, so an estimator is biased does not necessarily mean that it is a good estimator. It only guarantees that on average it will attain the true value. On the other hand, biased estimators are ones that are characterized by a systematic error, which presumably should not be present. Biased meaning that it has a systematic error. We do not like the systematic error, but in some cases, if it's inevitable, then we accept it. Right? A persistent bias will always result in a poor estimator. As an example, the unbiased property has an important implication that when several estimators are combined, it sometimes occurs that multiple estimates of the same parameter are available. So for example, you have for the same parameter, you have multiple estimators, theta 1, theta 2, all the way to theta n. A reasonable procedure is to combine those estimates into hopefully a better one. Hopefully mean sometimes we just cannot do it analytically. So hopefully it becomes a better one by averaging them to form, like you take the average of the estimates. Assuming that the estimators are unbiased with the same variance and uncorrelated, then if you take the expectation, you still get theta, which is unbiased. And then uh, you take the variance. The variance is giving you variance of individual estimators summation together divided by n squared. Then it will be, if they all have the same variance, then it will converge to what? It will converge to n variance of theta 1 hat, right? This whole thing. And then divided by n squared, it becomes variance of theta 1 divided by n. Okay, divide by n. So that as small estimates are averaged, the variance will decrease because you have n in the denominator. So if you have more estimates being averaged, the variance will decrease. Ultimately, as n approaches infinity, theta will approach theta. The theta head will approach theta. However, if the estimators are biased, or let's say expect of theta I is equal to theta plus some kind of bias, then estimate of theta head will, you do the same thing, and then you get theta plus bias. The bias is uh it exists always, and it does not disappear. Unlike this, this disappear with increase of n, but this thing doesn't disappear. And no matter how many estimates are averaged, theta will not converge to the true value. So it will be in the figure. And notice that in general, this expect of estimator minus the true value is termed as d of theta, that is identified as the bias of the estimator. So let's see, if you have unbiased estimator, it's concentrated around the true value, and you have a lot of those estimators, and you combine all of them as they increase, you get the outcome, the eventual estimator to be more concentrated. Uh, on the contrary, if you have a biased estimator, it is what? It is you expect of theta hat is the true value uh, deviates by some kind of bias b, right? It's biased, and if you have multiple of the theta and then you combine them together, as they increase, you get it more concentrated too, but it's concentrated uh, around a value that still has deviation b. It doesn't, this e theta hat doesn't go to theta. It still has deviations, and that deviation doesn't go away because of your increase of n. It doesn't go away, and that's the problem. So that bias seems to be giving us uh, a lot of trouble because the bias doesn't just go away. It will persistently exist in your estimate no matter how many you combine. So yeah, so I think that we end the session here.